Good afternoon, everyone. My name is Tom Tadero, and this is my great honor to be here to present my research report at this conference. My research is geographic mapping and knowledge-based negative cost estimation for direct air capture CO2 utilization. And I'm the second year of the PhD study at the Musashi University. And also I'm serving as a managing director of Global South Japan. And my today's presentation overview, starting from solving social problem. It's really climate change, CO2 removal, and utilization by the direct air capture in DAC. And my data science benefit is combinatorial optimization process, and its key considerations be DAC location recommendation by distance calculation, constraint, CO2 intensity versus cost, and unconstrained, and balance of the volume, and indicative cost estimation and project prioritizations. And please allow me to present the video for a minute.
Global Thermostat has developed a unique and powerful direct air capture solution to address climate change at its source and unlock massive, more sustainable industries. It's now clear we have emitted too much carbon dioxide into our atmosphere. We urgently need to remove billions of tons of this greenhouse gas to successfully address the climate challenge and rapidly replace fossil carbon with air carbon to power our economy.
Global Thermostat's patented direct air capture technology is the key to large-scale, low-cost carbon removal and the next industrial revolution. In simple terms, our solution works by using highly efficient fans to pass large volumes of air over high surface area contactors coated with a proprietary substance that naturally attracts CO2. We then use low-temperature heat to separate out the captured CO2 and repeat the process all over again.
Why I am doing this research, and my career started in the early 80s. Yes, I feel God, and I contribute to the economic development of the countries with the fossil and gas resources. So you can see the map, and the company name JGC I used to work for is specialized for the engineering, procurement, construction for the oil refinery and liquid natural gas. And some locations have been assigned, may be familiar with you, Pertamina Checkup, Singapore refining in Geelong, and Pertamina Alun Aceh, and Petrosobinso. And after 40 years, I realized my contribution to the oil refinery and liquid natural gas project is actually causing the source of the CO2 emissions. And we must, as you may know, we must remove the CO2 permanently from the air. And on this chart, and we are always talking about how to reduce the CO2 emissions. The technology I'm currently focusing on is how to remove the CO2 already accumulated for the last 100 years. So we need to understand CO2 reduction technology and CO2 removable and the negative emissions. And my technology is focusing on the CO2 removal. Of course, we need a CO2 reduction effort as well. So let's summarize the big picture and CO2 reduction and CO2 removal, and I explained from the previous slide. And direct air capture is a part of a negative emission technology. And that's alternative the front trees and the backs. Then once the CO2 has been removed, we have two ways. One is stored in the under the ground, we call it geologic sequestration. And its annual potential market size is 3.6 trillion US dollar by carbon credit. The other way is utilizing a CO2, capturing the CO2 from the air. And global market is about 1.5 trillion. And today's research is focused on one of the applications, which is construction material, which is about 750 billion global market, and agriculture. Then in reality, as we know, 1.5 degree is goal, but it cannot be achieved at the current pace of the progress. And 2023, the only 10,000 tons globally, and only 18 units is operating. And by 2030, we need 1 billion. And by 2050, we need 5 billion tons to be captured from there. We are far behind from the original schedule. Data science can support to accelerate the dark acceleration. But the point is, what's lacking from now is industry-specific practical data is not available. Easy-to-use tools and methods is not available. Data-driven justification is not yet. And everyone talking on the global scale, but no micro and local perspective. And the balance of quantity consideration is out of the consideration, unfortunately. And sharing economy model is also for the lack of the consideration. We need a solution for this. So my research framework, and at high level, and that is here I present on video. And to operate the DAC, we need electricity. And once we capture CO2, CO2 is needed to be transferred to the location to be used or to be stored. So this is the whole players to be involved. So we need renewable electricity, great. But if the renewable electricity, the solar and the wind generator is not available, we need to use a fossil-based electricity to capture the CO2. And once CO2 captured, we have to transport it. So this is the whole picture. And framework is the goal is we need to identify suitable dark siting location and cost estimation and for the tools. And this is system architecture. And on the other hand side, we need to acquire data. And also we need to put our industry knowledge into the table and combine two together by the computing skills. And we need to calculate the distance, cost estimation, and optimization, and share the environment. So this is the system architecture. And this is one of the sample of the screen of the output of our prototype system. This is the Tokyo region area. And let me explain to you how it works. So yellow is the concrete plant. And green dot is electricity. So electricity is everywhere. And concrete company is distributed some locations. And our algorithm can say, this is a good example. This is a purple triangle can tell us where the duct should be located by cost consideration. And this is, you can see 1, 2, 3, 4. And these 4 is each plant is 25 tons. And that has the 100 or 200 to 300. Let's say 100 is a DAC maximum size. So the 4 location is sum of the 4 location is equal to 100 tons. We can put in that one DAC unit. And if we exceed the 100, let's say if you choose 1, 2, 3, 4, 5, it's 175, it's exceeding 100 tons, so we need 2 DAC units. So this is a kind of the combination of the location. And once the system is calculate the optimum location and also the grouping, optimal location, where the duct should be and where the plant should be selected and which electricity we have to use, and all calculate by distance calculation and weighted factors. And system can tell us the option number 1, priority number 2, number 3, and each option the system can display the logic behind why this location has been selected. And the process is back to the system architecture, acquires location information, setting the KPI, and constraint adjustment, the carbon intensity versus the cost, and distance calculation, balance calculation, the supply and the demand, and the grouping consideration. And all together, and I try to apply the existing genetic algorithm or the dynamic cropping, but the system itself is a kind of combined 2 concepts of the algorithm. It put into my self-made algorithm for the proof of concept. Now this is sample location data and calculation of the knowledge into this formula, and can specify the 1 KPI, which is the knowledge-based cost estimation term. This is the indicator to evaluate the locations. And this is knowledge transfer, and this is industry data, I'm sorry. And we picked 1, 2, 3, 4, 5, or most important influential factors to transfer the knowledge into the CO2 per ton. Then let's go back. And this is the Tokyo metropolitan area. Yellow is the concrete plant, and renewable energy here, fossil-based energy is the gray. And we have 100-ton DAC. How many DAC we need? Where to start? How to group it? That is the puzzle. And my system has a logic behind. But the system is not it's not easy. Let's say green is electricity, and this is the concrete location. If we put the DAC at yellow location, yes, we can do that. But if you use the fossil oil, it's the same as this model. However, we are using fossil electricity is emitting the CO2, so we have to put a penalty on that. If we put the DAC at the renewable energy, let's say solar panel location, it's great. However, the CO2 captured here, and this is a concrete plant. We need to transport the CO2 by truck or the pipeline from this location to this location. So this is additional cost to that. And if we use the fossil oil, the penalty and all kind of penalty and the transporting cost is integrated into the calculation. And also for the shared environment, I explained to you before, the DAC is 100 ton per year, it's for 1 unit. So we group it 23, 30, 40, and the one group is total 100 ton. This will be great. But where the DAC should be, can be here, can be here, can be here. It's by the distance to the electricity. So all kinds of the constraint and constraint item is involved for the dot. And I did some experiment and the real data of the Tokyo metropolitan area for the concrete plant. And I specify the center location and I need to know where I should put the DAC. And I can set up the radius in here to 50 kilometers. And the system can automatically identify grouping and identify the location where the DAC should be. And also, this is the option. It's option number 1 is this one. And option number 2 is, let's say it's the same location, but DAC location is moving to this location. So number 3 is here and number 4 is here. So it depends on the total cost of the CO2 ton by sorted by this. And if I change the central location to here, and I'm sorry, then totally different, the grouping and selection has been identified. And I use the greenhouse, same here. And the result is we successfully completed the verifies the system functionality and accuracy. And this system can be expanded globally and also the other common applications. And my future research this time, my coverage of the research is we use a concrete and a greenhouse, but we can expand to the synthetic fuel or sustainable aviation fuel. And also the cost is moving to the improving year by year. So I need to apply for the kind of learning by doing method using or apply for the solar panel. Then I can project the future of the location or optimal location in the cost of estimation. And once I create a whole system, and I'm talking about the DAC only, but this can be applied for the other NAD negative emission technology, such as afforestation, enhanced weathering, and BECS. And this is learning model. And this is a potential market for utilization and sequestration. And thank you very much. And Terima and do you have any question on the construction criticism? I'm happy to make any answers and response to you. Thank you very much.